Hi, in this video, I am going to show you how we can use simple simulation to understand the concept of expectation value. So let us first define the system that we are going to deal with. Let's assume that there is an unfair dice. Now this dice is unfair because it can show up numbers 1 to 6 with different probabilities of occurring, uh, as you can see over here. And the experiment that we are going to uh, define is rolling this unfair dice once. We will also define a random variable s, and this variable is defined as the value that shows up when you roll this unfair dice once. Here, the range of the variable s is a set of numbers 1, 2, 3, 4, 5, and 6. And the question that we are interested in answering is, what is the expectation value of this variable s? So as I have shown in one of my earlier videos, how to calculate the expectation value of any given variable. And so if we apply that rule, the calculation is as follows. Expectation value of s is summation of s times the probability of s for all values of s, and which means that we have to take each of the possible values of this variable s, like 1, 2, 3, 4, 5, and 6, and multiply each of these values with their respective probabilities. So the calculation will be 1 times the probability of 1 occurring, which is 0.1, plus 2 times probability of 2, which is 0.1 again, and so on and so forth until 6 times probability of 6, which is 0.3. So if we do the calculation, it will turn out that the expectation value for the variable s is 4.2. What we are going to do is we are going to answer the same question, what is the expectation value of s, by doing a simulation. So let's go across to an MS Excel sheet and then look at how we can do that simulation, and we will compare the simulated data versus the theoretical expectation value for this variable. Okay, so we have the Excel sheet in front of us and we are going to do the simulation here. So this is how the unfair dice has been defined. For each of the possible values of s, the probabilities of occurrence of those values has been indicated in blue. All right. And some of the column headers I've already put well ahead in time so as to save time. And I have also numbered the entries in this particular row from 1 to 10,000 because we are going to do a simulation of 10,000 experiments. And in each experiment, we are going to roll this roll this dice once. All right, so what we are going to do is we are going to do two things. First, in this particular column, we are going to generate random numbers from 1 to 10. And we are going to partition these numbers from 1 to 10 in such a manner that we get the outcomes of the unfair dice. So let's see how we can do it very simply. Let's go ahead, generate the random number here. So equal to rand between 1 comma 10. And so there you go. The first random number generated is 3. And what I'm going to assume in this particular video is that you have already seen my earlier video on how to go about copying and pasting formulas and how to calculate or rather how to generate random numbers and how to use the if and rand between statements and so on. And the link to that particular video has been given in the description of this video. Okay, so now we need to copy and paste this formula in the entire column over here. So let's do that quickly. Okay, so there you are. So now this entire column contains random numbers generated from 1 to 10. And so now let us do the actual coding of the partitioning of these random numbers such that we get the possible outcomes for the variable s, meaning the outcomes of the roll of this unfair dice with the probabilities indicated in blue. So what we say here is equal to, if the number that is generated is less than 4 and this cell happens to be C6, so we say if C6 is less than 4, then consider that we have got 1, 2 or 3, meaning ran between 1 comma 3. Else uh, if now the same uh, cell C6, if the value in C6 happens to be less than 8, then we will say that the outcome of the unfair dice is 4 and 5, meaning we have to say rand between 4 comma 5, and if none of the two criteria satisfy, meaning it's not less than 4 and it's not less than 8, meaning that the random number generated is 8, 9 and 10, then consider that you have got 6. So we'll close the two brackets which we have opened, press enter. Okay, so there goes the outcome of the first experiment, wherein we have rolled the dice once and we have got 1 over here. So let us copy and paste the formula in this entire column now. Okay, so these are all our possible outcomes. And just to remind you, if you can keep pressing the F9 button, then the whole sheet will recalculate itself. And that we have already discussed earlier. So now the question is, how do we know that our coding is actually right? So let's find it out. So what we will do is we will just put the possible values of S in this column 1, 2, 3, 4, 5 and 6, and we are also going to find out the frequency of the occurrence of these values of S, meaning how many times we got 1, how many times we got 2 and so on. So we can find out the frequency in one possible way, which is using the countif function equal to countif, and we need to give the range, and the range is $d$6 $d$6 to $d$10,005, and we have given the range. Now we have to tell what is it that we are wanting to find. We wanting to find the value of 1, and value of 1 is entered in G6, so we say G6 and then press enter, and there you go. So what it shows is that 999 times we got the outcome as 1 when we roll these unfair dice. So likewise, let us find out the frequencies of getting 2, 3, 4, 5 and 6. We will copy and paste the formula in this entire column, and so here we are trying to find out how many times we have got 1. Here we are trying to find out how many times we have got 2, which is entered in G7, how many times we have got 3, 4, 5 and 6. All right. So now we can use the frequency data to find out what are the probabilities of occurrence of 1, 2, 3, 4, 5, and 6 based on the simulated data. And that we can do by simply dividing the frequency with 10,000. So let's go ahead and paste the formula in all these cells. So now let's examine, is everything all right? Now, if you see, the probability of getting 1, 2, and 3 are very close to zero point 0.1. They will not be exactly zero point 0.1 because at the end of the day, this is, after all, a simulation. But we see that the probabilities of occurrence of 1, 2, and 3 are very, very close to 1. Similarly, the probabilities of occurrence of 4 and 5 are very close to 2. And the probability of occurrence is 0.301846, and this is very close to the uh, the the desired probability of 6, which is 0.3. So meaning that our simulation has gone all right. So let us verify whether we have 10,000 experiments here. So if you sum up all the frequencies over here, we should be able to get the value of 10,000. So let's say sum for all these numbers. Okay, so there you are. You have got 10,000, and when you use the same sum formula for this column, uh, then you see that all the probabilities are also adding up to 1. So the simulation is fine. Now let's find out the answer to the question that we are asking. What is the expectation value of S? Meaning that if we are to do this experiment 10,000 times and these are the values of S that we have got, what is the average? Meaning in the long run, what will be the average value for this variable S? So we can find that now. So we will say expectation value of S, and that we are going to enter in this cell over here, and we can use the average function, average, and the outcomes are from D6 to D10005. So let's put that $D$6 colon $D$10,005. Okay, well, the average of the possible values of S, or the average of the outcomes that we have gotten in this simulation, is 4.2417, and this is almost the expectation value that we calculated by doing the theoretical calculation. And as per our theoretical calculation, the expectation value of S is supposed to be 4.2, and this simulation exactly shows that. Well, it cannot be 4.2 exactly because we have the simulated data with us, but then this whole exercise shows you how we can use a simple simulation to figure out the expectation value of S, and how we can tally that with the theoretical value for the expectation value of S.